In the previous video, we began the proof of proving that the closure of S is, in fact, equal to the set of all limits of sequences of points of S that converge in E by proving that the closure of S is a subset of this set L. This set L is, in fact, the all limits of sequences of points of S that converge in E. I just labeled it L for short. Now, in this video, we're going to prove that L is a subset of the closure of S. So now, let X be an L. If we want to show that L is a subset of the closure of S, then we have to show that if X is an L, then that implies that X must also be in the closure of S. So, if X is an L, let's kind of think about what that means. Well, X is in fact a point. X is equal to is a point that's the limit of a sequence of points in S. So, X is the limit, as n goes to infinity, of some sequence of points, an, such that a1, a2, a3, namely the sequence of points represented by this an, all lie in S. So X is equal to this limit as n goes to infinity. This sequence, in other words, this sequence, all of whose points lie in S, converges to X. Now, let's note down something. S is a subset of the closure of S, no matter what. In any case, S will always be a subset of the closure of S. And moreover, I've talked about in a previous video, that the closure of S is closed. It might seem trivial, but it's not too trivial. But the closure of S is closed. So check out what we can do here. I'm going to unveil the following theorem that's going to come in handy. And this theorem I'll in fact prove in a separate video. Here's the theorem that makes proving this statement up here, that L is a subset of S, much easier. So let's talk about what this theorem is saying. So let X be a subset of a metric space Y. Then X is closed if and only if, whenever P1, P2, P3 is a sequence of points of X that is convergent in Y, the metric space in which X lives in, then the limit of this sequence, all of whose points are in X, is in X. So what this is saying is if I have a metric space Y here, so this is my metric space Y, and maybe I have my set X here, then this is saying, well, this is dealing with the following issues. Like sometimes I could have a sequence of points that converge, but the limit of that sequence is a point outside of the set. But what this what this theorem is saying is that will never happen if the set in which the set of points lies in, the set in which the sequence of points lies in. So if all of these points in the sequence lie in a closed set, then the limit of that sequence will always be in that closed set. The limit of that sequence will always be in that closed set. So what we can say here, so this is X right here. This is X, just to be clear. So this is our closed set. And if I have a sequence of points in that closed set, any sequence of points that I take in that closed set, the limit of that sequence must be in that closed set. So check out what I have here. I have that X is in L. I have X is in L. Therefore, X is the limit of a sequence of points, all of which lie in S. And since S is a subset of the closure of S, therefore all of these points, A1, A2, A3, and so on, all of these points lie in the closure of S. And check out what I can do here. This is where I can use this theorem. I know that the closure of S is closed. I know that the closure of S is closed. And since I have a sequence of points, all of which lie in the closure of S, because they lie in S, and since S is a subset of the closure of S, they must therefore lie in the closure of S, then therefore the limit of this sequence, since it's convergent, must, by this theorem, lie in. So therefore, the limit of this, let me say it. Therefore, the limit of this sequence, which is x, must lie in the closure of S. And therefore, I've just proven that any point in L must also be in the closure of S.